Okay, so I'm just going to start out, and then most of this, will be hands-on stuff with CJ and with Kevin. So I won't bore you too long. So what we're going to talk about is we're going to be making a building. That's just going to be a video. Then I'm going to just go through the engineering design process briefly. There'll be a real-world example that I've worked on with a biodigester. And then CJ is going to cover making a landfill liner, and Kevin is going to cover a mousetrap car. And those are hands-on activities. And then if there's time, or if you still have energy, you can have questions and comments. I suspect that'll happen all the way along. And in fact, I think there's enough time that if you want to interrupt us, that's fine too. So don't hesitate to do that. Okay, so I'm going to show the video, or at least attempt to. Redirecting you to. Oh, is it? Okay. Okay.
Determining the structure of a skyscraper is complex and technologically challenging. Engineers rely on a step-by-step design process to guide their work. So, where do they start? Identify the challenge.
Designing a building is sort of like any sort of problem solving. You first need to identify what the problem is you have to solve.
The building is like the end of a process. It isn't the beginning, it isn't the start.
Once the design challenge is identified, engineers are ready to do research and brainstorm.
Brainstorming is a vital part of the process because as you design a building, you come up with new ideas.
In my experience, the first solution is never really the best one. In the process of brainstorming, I get different ideas from different people.
While researching, engineers weigh the benefits and costs of each design decision, both to the project itself and to society. These considerations are called design constraints.
I have this phrase that I use as a guideline for my work, and that is, a building must be safe. S-A-F-E. Primary, it must be safe. Safety is important. A stands for, it must be aesthetic. It must look good, and it must suit the needs for which it has been designed. F, it must function properly. By functioning, I mean it must have sufficient size and shape and access and so on, so that people don't feel somehow uncomfortable. And E means there is an economic side to it. That I must make sure that at the end of the day, the price that it's supposed to cost, that's what it costs.
The next step is to design a solution. Engineers use the information from their research and brainstorming sessions to come up with a variety of possibilities to solve the original challenge. They then make drawings and plans outlining their ideas. But how do they know that their design will work? They test their ideas.
For engineering, testing is very important.
We need to make sure that what we're doing is going to stand up against the forces that act on it.
Engineers build a prototype or model and then test the prototype to make sure it will stand up against load or forces that will act on the structure, like gravity and wind. What comes after testing? Evaluate.
To evaluate it means that you have to take a look at your solution and see whether it solved the problem. We may give it to some other engineer who will check what you're doing, just as a teacher would check a homework problem.
The engineering team presents their solution, but if the design doesn't solve the challenge or satisfy the constraints, it's back to the drawing board. More research and brainstorming, new designs, and retesting. Only when they've come up with the best possible solution is the design process complete, and they're ready to build it.
Before you build a structure, you need to identify what tools you have.
Where are all my materials going to come from? Who's going to build it? How many people? And what skills do they need to build it?
And at each step in the process of building a skyscraper, engineers evaluate their work and the work of the construction team. Like engineers David Pravat and Susan Mack, you can use the step-by-step design process on projects of your own. Identify the challenge, brainstorm, design a solution, test ideas, evaluate, build it. The next time you look at a skyscraper, a bridge, your own school even, think about all that goes into building it. Think big.
Okay. So I think that is really a nice video, and you'll see this engineering design process done in different ways, or at least presented in different ways, but it's all really pretty much the same. And that's what I'm going to go over next. And you'll see this a lot. You'll have this in your classrooms. You'll hear it also from CJ and Kevin. And now, oh, there it is. Okay. So this is one of the cartoons that shows the engineering design process, where you start out by identifying and defining what it is that you're trying to do. Then, gathering information is very important. And in your classrooms, one of the things I've seen that's effective is when you have computers, having the students do internet research there on what they're doing, taking it home and doing work there. I forget what the programs are, but there are those sort of Blackboard things they can use at home that they can put more information in. Then, one of the things that's very important in the world that I came from was identifying all the alternatives. And that doesn't mean just alternatives that would involve a particular way of doing something, like I want a car to do this, so I'm going to make different cars in different colors. That could be cars, trains, planes, boats, etc. It's the bigger set of alternatives. And oftentimes you have to make presentations on alternatives to get the funding to do that work, because people want to understand the cost-benefit analysis. Selecting the best solution from that, and there's a lot of communication. You see that in the middle going on all during this process. This is communication, as we would typically say, down and up and sideways, because there's a lot of stakeholders involved. Then there's the implementing of the solution you come up with. That's really building it, kind of in the video that we just saw. Then evaluation, and then oftentimes refining. Now, obviously, you're not going to build a building and then decide to change it, but on the prototypes for that building that they talked about, you would have loops within loops here. So you would do that, test it, refine it, and eventually, when everybody was satisfied, and again with the constraints of budget and time, you would build the building. Okay, so that is one of the times you'll hear engineering design process. You'll hear it a little differently from everybody else, but after a while, this will become second nature. So I'm going to switch now to some of the work I've been involved in with Engineers Without Borders. I'm currently a vice president of our local chapter, Greater Cincinnati chapter. We also work with the UC chapter, the Miami chapter, and the Wright State chapter. And one of the projects we're involved in is in Uganda. This is Busesa, Uganda. And this is a school that is operated by the Sisters of Notre Dame, the same ones that have the school in Reading. They've done that since 1995. They've been in this location. There's about 500 students there. The school has a farm, and I thought it'd be interesting to just understand how it is in Uganda. The life expectancy average is 54 years old. Half the population is less than 15 years old. And the reason is AIDS. AIDS has been devastating in Uganda. 67% of the population is below the poverty level, and the poverty level is $1.20 a day. And so one of the things they need that you'll see in this slide is they need a safer way to cook. If you take a look at that, you're getting a lot of smoke. You don't have enough ventilation, and so really from an indoor air quality standpoint, it's not a very safe environment. The other thing is that wood is becoming more scarce, and as a result of that, there's a need for alternative energy. Yeah, I don't know. We're trying to turn down the lights so we wouldn't, so you can see it better.
No, like on the
Oh, here.
Oh, there it is. Yeah, there we go.
Is that better?
Okay. Yeah.
That
No,
better.
that's good.
People see better.
Can you see it in the back? No, it's still not? All off? Too dark?
We can see it
Now we can see it.
Okay. So you can see it's just really a nasty environment. Okay. So anyway, in the context of the program that you're in, here the big idea is clean energy in the developing world. And the essential question is, can biogas from farm waste power the kitchen for a school that feeds 500 students and maybe even the community also? So let me take you on a brief part of the journey that we went on. So this is what I did first. So what ended up happening is we spent a lot of time talking about how we would build a biodigester in Uganda that's fairly large. And one of the things that we concluded was we needed to understand how anaerobic digestion would work before we were ready to do that. So a very quick course on anaerobic digestion is you put waste in. It can be animal waste, so they have goats and pigs and rabbits even, and so you can take that animal waste and then you can load that into a reactor, and then you can put plant material in there, and after a period of time it will proceed from having oxygen in it to having no oxygen in it. And once that happens, you can get organisms called methanogens produced, and those methanogens then produce methane, and I think everybody probably knows you can burn methane. So it becomes good cooking gas, and when it burns, it's clean as opposed to the wood. So what ended up happening, and this is kind of why, one of the reasons why I wanted to talk about this, what ended up happening is that we were working also in partnership with the Cincinnati Zoo. The Cincinnati Zoo got wind of what we were doing, and they decided at that time that they wanted to have one too. And they thought it would be neat in the new African exhibit to have a biodigester along with the one we were building in Uganda. So I was told that we had literally that evening to put together a schematic of what we would do. So you can see this is pretty crude. This is all hand drawn, but I sent this in because of the urgency we were under. And to make a long story short, the zoo kind of just forgot about it. We don't know how we went from urgency to no urgency at all. But because we kept believing that they were going to do this, we started work right away. So from the standpoint of looking at alternative ways to make it, we kind of went pretty fast. And in retrospect, like many things that you do, and again, as you think about your classrooms, this is what ends up happening. You can kind of go quickly when you should have taken a little bit more time. It worked out okay, as you'll see, but there were some things we might have done better. So here we are doing some building. We ended up, the fellow on the right was able to find these tanks. He works for Dow Corning. Lee Height in the middle there is a master builder. This guy can build anything in his shop. And so we went and started building the biodigester from spare parts and Home Depot. Lots of trips to Home Depot. And here's Mark doing some cutting. Here we're doing some fitting in here for what's called the gas collector. I'll describe this a little bit more at the end. And then this is the finished digester part of the apparatus. Now, the reason I put this slide up here is just to illustrate how important it is to document what you do. So, in the world that in the practical engineering world, the temptation is, you always do this, but you're always hoping somebody else will take the lead on it, because documentation generally isn't something people love to do, but it's extremely important. So with this diagram and a lot of tables and things like that, you could reconstruct this completely. And you could also, look at the parts and see if you had something better than that. So just wanted to make that point. Now, when we did this, one of the things we found was that we had a troubleshoot on the way. And I call it troubleshooting. I think this was sort of the evaluation. We wanted to make sure this would hold pressure, because it's very important to commission your machinery or your apparatus before you actually use it. And for us, if these leak, you can get an explosive hazard. Because if you get oxygen in with methane, what happens? Well, you now have a combustible mixture. So you want to make sure that these are pressurized so that the flow of gas is only out and not in. And so pressure is very important. So I'm just going to diverge for 1 second in a different area and give you an example of why this is so important. So Jack, Tom, and I work at the Green Learning Center. And Jack and I were there one day recently, and we had been working on irrigation systems for gardens. And with those systems, we had tanks to collect water, and we also had irrigation systems that were kind of trickle systems that you may have seen, where just a little bit of water comes out and you can irrigate the whole garden. And this saves money, and it's environmentally friendly, et cetera. And we use solar pumps. Neither of the solar pumps worked. So Jack and I took a look at the first pump, and we found there were a lot of fittings that weren't right. And one of the problems with that pump was that it was already encased without being commissioned, and the cases ended up having to be taken off in order to figure out what was going on that was wrong. In the second case was a bit more dramatic, where we had the system set up, and this is the bigger of the two. There were about half a dozen big water collectors and a roof over them that collected the water in the middle, and there was a solar pump. The solar pump, again, didn't work, and we couldn't figure out why, and it seemed like it was clogged. It's a brand new pump. It didn't make sense, whereas the older one was an old pump, so we thought that might make sense. Didn't need to be primed, so we were kind of puzzled. And I stuck my hands in there and tried to fiddle around, pulled the fittings off and looked and all of that, and then stuck my hand into the fitting in the pump. And it was blocked, okay? This is why it was blocked. I don't know if you can all see that, but this is a little plug that was in that fitting. And then on the effluent end, the same thing was there. So it still didn't work, and there's the plug. So we had two plugs that we found that were in that line. And here it was covered up in a nice covering so it wouldn't be vandalized, and it also wouldn't be exposed to the weather. And nobody had checked this ahead of time. So it's just a good example of where you've got to do your homework. And from your sake, when you're in the classroom, one of the points that you'll hear several times is that check to make sure that your experiment or your activity works before you give it to the students. Because even if you want them to fail, and failure is very important to learn from, you want to understand what's going on ahead of time so you can help them. Okay. I think you can see it. So here's the almost finished digester. This is the digester part that you saw. Here's where you feed it. Here's where you take the effluent out. And then this big tank here is filled with water. Now you'll see in the next slide it's filled with water, and that rises because this bottom here is hollow, and as the gas comes out, it fills up, and then you can burn that gas. And that's the idea. These bubblers are here to arrest any flame that might try and come back through. And they also scrub the air so it doesn't smell. And then this is the finished digester. One of the things that was very important here is we had to satisfy the regulators. And in this case, the regulators were the fire marshal. Because here's a device sitting right next to a building, and how do you know that it's not going to result in an explosive mixture? And so we had to do some, we consulted with somebody who had done a lot of this before. She suggested that we vent up over the roof, so we built this. I built this manometer with my son, who really enjoyed it, and he's got some special needs, so this was a great thing to be able to do with him. And then, we showed all of this to the fire marshal, and he was satisfied. He said, but what about having a fire extinguisher? And he just suggested it, which was great. And as soon as if you talk to anybody who's in a position like that, if there's something you can do right away, it ends up greasing the skids, and it's a better conversation. So I said, yes, we'll get a fire extinguisher, and I put it on the next day. So again, this is something that was important. So just to wrap up and kind of cover what it is that I had talked about. No, that's not the right one. So the big idea here was clean energy in the developing world. the challenge was a village-sized anaerobic digester. That's the bigger challenge. This is just a test digester. So the sub-challenge is that we identified what was needed. We looked at different designs, and we didn't do this enough, but we did do some of that. We made some changes. We looked at alternatives for the bigger project, and we've spent a lot of time looking at different ways to do the bigger project. That, this is about a 45-gallon tank, so it's roughly 200 liters, and so at 0.2 of a cubic meter. And we're looking at a 50 cubic meter tank for Uganda. So it's a much bigger, it's not going to be a tank, it's going to be in a big bag that swells. So we continue to look at the best solution there, and then we went ahead and built it and implemented it. And it is, if you're curious, it's on its way to producing gas. It's not there yet, but it will get there. So that was it for mine. Now, we'll go on to CJ. Oh, sorry. So any questions before we go? Because I think we're good on time. Okay.
Sorry if it makes you uncomfortable, but I can't stand behind the desk. So I'm going to be walking around. From a teacher perspective, you guys are going to start making your units and everything, and I'm just going to tell you now, they're going to take longer than you anticipate. Like, this process takes a while. And the first time you do it, it's going to be longer than when you do it again and again. So you'll learn, and you'll see, I've kind of chosen a format that works for me, and we'll go through that process together. We're going to have to, for this identify and define thing, just kind of pretend like for now that we've already talked about water availability on Earth. You know that there's a very little amount of water available to drink, and that we all make garbage, we send it somewhere, it rains on that garbage, and we want to keep that garbage out of our water. Okay, so I'm not going to spend a lot of time on identify and define. We could do a whole workshop on just that. Just what kind of questioning techniques are you going to get the kids engaged, and then sell them on the idea that they came up with this challenge on their own. And you'll learn that from Michelle too, because when we first did it, we were like, oh wait, we're going to let them choose exactly what they want to do, and then I have to go buy all the supplies for that, but there's some type of leading that goes along with that. You're going to take all their ideas and then clump them together and go, they fall under this category, and then you'll say, oh, I have all the stuff here for us to do what we just decided. So again, that is a whole, and everyone does it a different way. That's why I'm not going to spend too much time on that. So if you can go to the next one. So identify and define, we know that we make garbage, we know we send it somewhere, and we know that it rains on the garbage. It goes into the ground, to groundwater, and a lot of us get water from the ground. So we have landfill liners, they're massive. There isn't a machine big enough to make just one solid sheet of it, so they have to make individual pieces and piece them together. So that's kind of the problem that we're at. And then, I should probably pass this out to you. Okay, so who is actually, this will give me an idea of the numbers too. Because I'm going to start referencing the sheet here. We got 3 here, 2 here. And now that I look at all the computers, we're going to be using water and pouring it. So I take no responsibility for damaged computers. I don't think the IT department would like it either. All right. Do me a favor. On the front page here, you'll see that there's just some background introduction information. And if you could turn the page over, you'll see on the inside there are some warm-up questions. This would be like if usually I have the class come in and have some type of like bell work or warm-up thing so I can prepare all the materials, because when I have one class leave, another one's coming in, and I need time to set up and I need them to do something. So here, turn it over again, because now that we've established kind of the challenge that you'll be doing, you let the kids gather information, and you'll notice it's just a blank sheet of paper here. I'm sorry, it's this blank one. I think I put page numbers. Page number 3. Yes. Oh, I'm sorry. Here you go. Here, I already turned to the page for you. Okay, so I've introduced the challenge to you. You are going to be making a landfill liner. It's not going to leak. You're going to try to prevent it from leaking. And then I would have the kids go and gather information. Now, in a lot of your units and activities, you're already going to be giving them information that they'll be provided with, right? But then you'll reach your final challenge where, and I want to be clear on this, for your activities, for my activities, I do not do this whole engineering design process for every single one, because then it would take me the whole year. So I save this for the bigger challenge that we're doing, the big thing that we're working towards. And I did not choose my big challenge from my unit, just because the materials that I would have to haul in here would be crazy. It was like rocks, it was stones. They actually made a landfill, and they had different materials to make the landfill, and then they put little cotton balls with soaked in vinegar, and then they rained on it, and then they dug in the ground, and then they tested the pH to see if the pH of the groundwater had changed, because vinegar has a different pH. So for me to haul all that in here, that would have been crazy. So what I did is I chose one of the activities that gave them information to help them with that activity, and then we're going to do the engineering design process using that activity. Does that make sense? Okay, all right. And I do not do that for every activity. So I give them time to gather information. So at this time, I would say, all right, we're building a landfill liner because we want to keep that garbage out. You're going to have strips, you're going to put them together, and we're going to be pouring water, and you're going to try to keep them from leaking, to keep that garbage water out. And then at that time, I would say, all right, we've done some lessons on it, but now you guys can go and look up your own information. And if you don't feel comfortable just sending them loose on the internet, then this would be the time where you give them the information, different sources that they can explore. I'm comfortable enough to let them do it because they like to be, they like to try to be sneaky, like, oh, I'm just gonna look up the answer in Google, and they'll type up the whole first sentence, or they'll type up exactly what we're doing, word for word, and they'll hit enter, and it'll be 0 search results. And then they get really excited if they find something really similar to what we did. So when you're making your units, and if you're taking a cookie cutter activity, I'm encouraging you to change it, because if they do go home and just like look up an answer or something, it loses its challenge. They lose their motivation. So make sure it is actually a challenge and the answer isn't just there available on the internet. Okay. So I would set them free, and at this time, you would be looking up landfill liner designs. You'd look at how they piece them together, and then you would not be allowed to talk to each other at this point. Okay, this would be your own individual research. And this blank sheet here would be for you to draw pictures, for you to write information, for you to pretty much be able to, because after this we're going to share, you would share with each other what you found, and everyone should have something to contribute. So this is where you would do that. If you could turn the page again, so you've done all your brainstorming and everything, you should be looking at a chart. So you've gathered information. And then you're going to identify alternatives here. So for the alternatives, you've done your individual brainstorming, you've gathered your information, you've used stuff that you've learned in the activities that were already there. And then for the alternatives, you would take turns sharing what you found with each other. And you'll notice that it says design 1, 2, and 3. At the end of this whole conversation, you would have three different designs that you could build and test. And the way it would work is you would take turns saying it. The other people are not allowed to saying what you found, and what your design is and what your ideas were. And you would say, all right, here's something I found. I think we should do this just side by side. I think we should lattice it. I think we should do all these other things. And I would talk to you and show you what I found. And then you guys would try to get down the information that I found. And then I've shared it with you. And then at the end of me sharing it, you could ask me questions if you wanted to. But you're not allowed to interrupt me while I'm doing it. So honestly, I keep it very structured. So the first day, I'm like, here's what the challenge is, here's what the materials are, go free, gather your information. And then the next day they come in, and then they go through the sharing process. Like I said, it takes a while. So then we would end, and I would tell you what my pros and cons were, and then you would tell me what you think the pros and cons were, and we would have that first design filled out. And then the next person on the team would share what they found, and then I would make sure that I wrote down everything that they found and what they think we should do, and then we'd talk about the pros and cons of that design. So at the end of this, we have 3 designs that we could potentially build and test, which is great, because it's everyone sharing, everyone can find information, everyone can contribute. It's not like I'm on the spot and I can be like, here's the website I went to, just look. So for all your antisocial kids and kids who have trouble sharing and stuff, this was very beneficial to them. And I'm showing you this because if you just send them free and you go, pick a design, they're not going to have the social skills to be like, okay, I'm going to go first. Please don't interrupt me when I set that up for them. and it is really helpful for them. All right, so then after that, on the next page it says select an approach. This is where the arguing can kind of come into play. So for this, a lot of students have trouble picking a design because they have spent that much time thinking of their design, and they've shared it, they're committed to it, and then the other people are committed to their designs. I would say this would be the most difficult part of this whole activity, is them actually coming up with an idea that they're all going to build and test. Now, I make it clear at this point that they will have time to actually revise and redo it. So even if their idea isn't chosen, they might do it like a second time. I actually just encourage them to take elements of each one of their designs, incorporate it just to prevent fights or disagreements. I won't call it fights, I'll just call them disagreements. So you would, at this point, you have your 3 different designs, you would talk with your teams and you would say, I think we're gonna build this one first. And then you would come up, show me the design, and then you would actually start the challenge activity. So we're gonna have to get into groups here. How many people did you get a count? This will just take a sec. I kind of bounce around, I'm sorry about that. So identify the problem, the gathering information you did by yourselves. Identify alternatives, that was where you talked to your team and you came up with your 3 different designs. You've selected your best design. You guys are just going to do this right now. You're adults, we don't have time for all that. Implement the solution will be when your product is done, I'll show you how to test it. You'll evaluate the effectiveness of it, and then you would communicate the results. So at the end of this, we would say, all right, here's what I did, here's what worked, here were my results. And then if I wanted to refine the whole thing, we could use some of the lessons learned, like the successes of all the different teams, and then create a better liner using it that way. One way, you'll learn this in Michelle's class that I like, is to have, for the refine stage, you assign like one variable to be tested for each team. So you would say, this team is responsible for the landfill liner materials. This team, which means you would test different materials, right? And then I would say, you guys are responsible for testing different lengths of the strips. And then you guys are and then we would share out the information. And you'll learn this with the wind turbines. You guys will have one variable to test and you'll share it out. And then it just causes more investment, because then this team would be like, oh, they did materials, I should go talk to them. And then you have teams like talking to each other about, or if you can't remember like what was successful, and then they'll come over and ask you clarification questions like, oh, how did you have them aligned because you had good results? I really like that aspect of it, just giving a team like one variable, share it out, and then using all that information to make the better product, which is the way that engineers work as well. For this one, we're not gonna do that. But I'm just telling you, that's the way I like to do it. And then you'll notice that communication is involved in all of this. Okay, you probably want to get to the building part. Can you go to that slide that says, it's got the baby on it. All right, so then this is the part where all the kids are like, yeah, woo! We're gonna build and test these. And you'll notice that I left out some information on the procedures. I did that on purpose. Sometimes I won't give them the exact numbers on the paper, because if there are problems in other classes and I see they're struggling with it, I may change it for the next class. And if I have it on paper, the kids are going to hold me to it. They're going to be like, what's going on? So sometimes I will leave things out. You're going to have to add that the length of the paper strips, if you can add this now, is going to be 10 inches, the length of them. Or I'm sorry, the plastic strips, 10 inches. 2 by 10. Yeah, 2 by 10. This is also going to be a trust exercise. I am giving you the tape up front. If I were doing this in class, I would have the tape. Okay, so 2 inches. You guys got it? Number 1, you're going to take 5 2-inch wide, 10-inch long plastic strips with 12 inches of tape, and you're going to piece together your own landfill liner. And the way we're going to test these is you'll have pretty much like your landfill liner. It's not fancy at all. So those of you who don't mind your hands maybe potentially getting blue, you're going to want to be the holders of this thing. You're going to have your landfill liner. You're going to hold it in your hand. We're going to pour out 200 milliliters of water into this cup, and then you're going to hold it over this black. So I got my bag. I hold it in my hand. Someone else pours the 200 milliliters. We time for a minute. You take what's left in your bag, pour it in the measuring cup, and then we'll find out how much did not leak out of your landfill liner. You got it? That's why I said hide your computers, because this can get messy. And then if you can't tell what it is, there are some graduated cylinders in there. You can just measure out 50, 50, 50, and just kind of get your measurement of how much was left in your landfill liner. But for now, let's just focus on building them, okay? So if you could just read through the procedures and make a liner, then we'll test them. I didn't do it with you because you're adults. Assigning jobs is always a good thing. And one job that I really like that a teacher told me about is you'll find one group. There's usually one group that will just be so frustrated that they are not doing well or something, or they'll be like, I don't have any ideas. If you assign, like, just take a minute and say, all right, you're a spy, and then you just let one kid walk around and just spy on the other groups, it helps a lot. It's an easy job to do. I usually give it to, believe it or not, my behavior problems in class, and I'll say, you can't talk to them, but you can go spy on them. And then, the ones that usually get in trouble are the ones that need to move around anyway. And then they're going around, they have a sense of responsibility, and they get to bring back all the secret information to their teams. And then it gets that team jump-started again. It's just a classroom management thing. So jobs, I recommend it. Each teacher, whatever you're comfortable doing with jobs. And then another thing is, a lot of you were asking me, like, can we begin the redesign process right now? Now, you'll naturally, if we actually did go through the design process, you would have had your design, and then as you're building it, you would naturally redesign as you're doing it. Because I saw a lot of you taking the measuring cups, and then you started, like, draping it over the measuring cup to be like, oh, how much is 200 milliliters? And then you were redesigning in the process of that. But the real redesign process happens when you share out your results with the different teams. So it'd be like, I had 184 milliliters over here. Can you raise your hand? 184. Where were you at? So they had 184, and they would share that, and they would say, here's what we did. And then everyone's listening, and they're taking notes. And you don't even have to tell the kids to take notes. They're just doing it because.
Bree actually did that at the very end. She was showing the group in front of us.
Okay, so.
So we were doing that.
And some teams are really secretive about it, like while it's happening. Right, very secretive. But when you set it up in a class, like the teacher, if you set it up and you go, okay, we're going to share our results. Honestly, if you just say we're going to share our results, and then you go team one, they'll look at you like, So I always have guided questions up there. I'll have 1, 2, 3 questions. They're usually things like, what was your design, or what were your results? What was your design? What would you change? I can't remember that, but they would be up there already, and I would say, you choose in your team what you're going to answer. And then when I call on you, I'm going to say, team one, first question, and then each of them, they're responsible for presenting something. But I give them the prep time to do it, and they know what they're going to say, which is really helpful. Because, again, if you say, share your results, you're not going to get substantial information that's helpful to the rest of the class. And then we would do the redesign process once you've learned everything from the other teams. Are there any questions about that? Yes?
So they have to, whatever design they pick, they have to do that exactly. They can't change it.
That's the way I do it the first time.
Even if they know, like, part of the way through it's not going to work?
They have to get it approved by, I need them to have something to start with. And you'll notice that I do let them change, to be honest with you, because you'll notice on the next page it says, sketch, describe your final design. Because they will change. I know they will. And I guess I should have been upfront about that, but you guys naturally did that. Like, you kind of got to the point, you're like, uh-oh, right? When you started pouring it, you're like, this water's not going to fit. We just didn't have enough time for.
So you tell them they're not going to with any kind of later on?
I don't mention it, but if it comes up, I say yes. I just want them to be committed. And honestly, if you just said, all right, you're building, we would have gone through this process faster if you had already had, like, your stuff already sketched out. We went through that conversation. It took you a little bit longer because you had gone through those first few steps. I just kind of skipped them. I think that's it. And then you would redesign, retest, and we'd share out again. Are there any questions about the whole process?
I teach CP Math 2 at Milford High School, and it's a co-taught situation, so it's a little bit different from what I'm assuming is going to be a majority of what you guys see in your schools now. Does anyone know what co-taught is? Anyone have a co-taught class? How many people have a co-taught class right now? Only a couple? You did. Well, with that being said, I'm the general education teacher in the classroom, and then I also have an intervention specialist in there. The way that Milford does it is that we have 12 students in that class, between 12 and 16, that have IEPs or specific learning disabilities associated with reading or computation or anything like that. They're in this class called COTOT. And I fabricated almost all of my lessons for this class because I wanted to try something different, and I kind of had the room to do so there. I've noticed throughout the year that I kind of had to go through the engineering design process a little bit different than everyone else in the program because the kids were just a little bit different. They learned a little bit different. You guys will soon realize that you're going to have to adapt to your own style of teaching and how you implement this, as well as adapt to how your kids learn in your class. And that was kind of one of the harder things that I've dealt with. I pretty much have a good, strong grasp of it now after doing it 3 times last year. The kids, by the time they got to this unit right here, the mousetrap cars, they were working together. They weren't trying to beat each other up, which is always a good thing by the end of the day. And they weren't trying to beat me up, which is that's a plus as well, you know what I'm saying? So anyway, so that's kind of like the background that this lesson comes from. It is for 10th grade math. All the people I had in that course were sophomores. You can fabricate this lesson. It's based on linear equations, so you could do it for 8th graders that learn linear equations their 8th grade year. You can do it for freshmen. You could do it for sophomores in our CP Math 2 class. You can actually take this lesson as far as average rate of change in pre-calculus if you wanted to. So all the lessons that I created, you can span throughout 3 or 4 years of math. I didn't know what I was teaching last year until about July or August, and I had to formulate lessons for SEAMS. So I kind of created ones that I can alter just a little bit for each level of course. So I was able to use it for CP Math 2 indefinitely. So I'm going to go through how I do the EDP with these CP Math 2 COTOT kids and the other classes that I've done the projects in. This project is based on mousetrap cars. The main topic is linear equations. The relationship that I want them to get is distance versus time, obviously. They're going to take data from their mousetrap cars. They're going to go on Microsoft Excel. They're going to plot the data, and then they're going to find the slope overall, which is generally going to be their speed, if you will. But I had to prep them for this. As CJ was saying, you guys are taking Michelle's class right now, and she was spectacular about it. She did engineering design process in a way that we wouldn't fathom if we hadn't seen it from her first. You kind of prep them for it. You don't really tell them what's going on, and then you guide them to finding the relationship. Then you're like, oh, we can build cars. Here you go. So the materials and whatnot are given. I did show them this diagram, probably not as they were building, but a little bit after, and they're like, oh, we developed this on our own thinking. And I'm like, well, yeah, and I mean, that's pretty cool. So anyways, first activity that I did, they had no idea they were doing mousetrap cars. I did a tennis ball drop. All I wanted them to understand was a relationship between 2 different variables, whether it be height and time, distance and time. As you know, height and time is not linear. It's going to be a different relationship. So I just wanted them to see a relationship between 2 different things. All right. As long as they can find a relationship between 2 different things, they'll soon realize that there's differences in those relationships between multiple things. So with that being said, they took a tennis ball, they dropped it, and they measured it how long it took to hit the ground from a certain height. I took markings, I put them on the wall, they dropped it from 1 foot, 2 foot, 3 foot, 4 foot, and then they looked and they're like, oh, we have data. I had them actually plot the data on Microsoft Excel too, and they had a general shape that resembled that. That kind of prepped them, to see that there's relationships between 2 different things. I then kind of went into the engineering design process with them. I asked them in class, I'm like, what other things have relationships? And I kept asking and asking and asking. Almost everyone was like, well, you can travel a certain distance over a certain amount of time. My parents drove to Florida, it takes 14 hours. I'm like, well, that's great, there you go. All right, they're already getting along those lines of thinking. So I kind of prepped them. I'm like, you know what? I want you guys to build these cars. I want you guys to think about designing the cars. What's the main relationship associated with that? So this is for the engineering design process of activity 2, this is the chart that I gave them. I like it because it It relates to both of what they use too. It's a constant circle. You keep going back and forth and back and forth. You identify a problem, you identify the constraints, you keep going on, and then you have to start over again because you have maybe not as big of a problem, but you have a new problem that you have to deal with, and you have to refine your design to change it. So that's kind of where I went with that. This is the activity that we're actually going to do today. This is the main activity that I had for the kids. It's the building of the mousetrap cars. It doesn't take long, but the refining of it takes longer than I thought it would. It took 2 days to actually build these. Everyone had a prototype within 15 minutes of me giving them the materials. All right, so what I did first, before I even gave them the EDP, was I gave them these kits that I had built. I gave them the kits, I passed them out. All right, I let them tinker for a little bit. They had already developed the idea of distance versus time, so I passed them out to each one of the groups and I let them tinker. All right. The way that I look at it, these kids need something to get their hands on first in order to understand what the problem is actually going to be. After I let them tinker for about 5 to 10 minutes, I flipped back to my slide about engineering design process and I said, what's the problem that you guys are having? What's the main problem of the situation? And they thought to themselves, they collaborated with their groups. I was able to get a bunch of different answers from different groups and put it on the board, and we were able to go through it that way. So what we're going to do today, all right, I'm going to skip all the talking stuff so you guys can actually get to a unit that you could possibly use and how to implement it using EDP, is I'm going to give you these materials now, and I'm going to go ahead and give you 5 or 10 minutes to tinker. Feel free to do whatever you want with these. All right, I'm just giving you the kits, and I'm going to tell you, build a car, go. And you guys will see, you'll talk to each other, and you'll be like, what's the different type of problems that you're going to see, so on and so forth. So get back into the same groups that you were in. I'm going to break up one of the groups because I unfortunately couldn't carry 18 million pieces of wood because it's kind of heavy. So I only have limited materials. So I'm going to break up a group here. Hey, it's a learning opportunity for all of you. I came in thinking that we were going to be able to get a car running. We ran into some issues. A lot of people are being real meticulous about it, so on and so forth. Not a problem with that. What you guys need to realize is new teachers to the the SEAMS program is that when you guys create your lessons, the time frame might change. You're going to run into your lessons. You're going to be like, oh, shoot. I need a couple more days. All right, and that happened to me a bunch of times. I did the mousetrap cars. They were able to develop a prototype in about 15 or 20 minutes, as you guys did. But getting it running took a lot longer, in regards to getting it running at least 5 feet. All right, so that being said, you guys now have a lesson idea for you. To give you a general idea on how they actually work, this group did pretty good. I didn't have, whoa. Oh, wow. Oh, yeah, you did. Anyways, I didn't have a group at my school actually use all 3 mousetraps. They only had to use 1 and some rubber bands. All you do, you take this string, you bend your mousetrap backwards, and then you spin your axle around. It tightens, and then when you let your mousetrap go, guess what it pulls? The string and the rubber band and your axle. And it keeps the back parts of these moving, and it'll actually pull your car along. Now, if you notice that if you were to just use string and you were to put this on the ground, the wood's too heavy. It won't go. If you use the rubber band, it adds that extra oomph to it, and it keeps it moving. All right, that elasticity in the rubber band actually makes it go far. Now, I had a group, interesting enough, I had a group just use rubber band without a mousetrap, and they had it go almost all the way down the hallway. And I'm like, I didn't put that constraint in there, so I guess I have to let them do it. And I asked them, I'm like, can you do the same thing with the mousetrap? And they're like, you know what? Let's try it. I'm like, you guys got time. Why don't you try it? So they changed their design a little bit. They put the mousetrap, as I had just stated, rubber band. Instead of a string, they just used a series of rubber bands, wrapped it around the axle, and it probably went twice as far. So it was actually pretty cool to see that they were able to, take that guideline and use it as an extra source of power and kind of move through it. But for the sake of time, I kind of wanted to stop you guys a little bit early. I know some of you are getting a little antsy and you've been here all day. So do you have any questions for me in regards to that lesson? Anything at all? Right on. Well, if you have any questions in the future, you're probably going to see us a whole bunch, so